Hello guys. This is the capacitors in series and parallel tutorial video. For this tutorial, I'm going to start sort of the other way around. I'm going to show you the background that you need to know for the lab. And then I will show you the experiment or the simulation that you're going to use. And let's start. So with capacitors, remember that you can have them in series or parallel, right? So if you have a capacitor like this, let's call it C1, C2, and then C3. I will give you values as well, all right? But for now, the 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. That's how you find CEQ. Now, if this is plugged, if this circuit is connected to a battery, right? You have a voltage supply. Right? You have a voltage V. So the equivalent capacitance is equal to the charge on the circuit, the total charge, divided by the voltage on the circuit. So if you multiply C equivalent times the voltage supply, you get the total charge. Now, when you have capacitors in series, the charge is constant. Some of you may do this lab at the time when you have discussed properties of electric current. So current, right, that's for later for other type of circuits, but current is defined as the rate of change of charge or the first derivative of charge respect of time. Coulombs per second, amperes. So charge and current are proportional. We talk about current for circuits with resistors and also capacitors. Now, you just have capacitors. There is no really a current, right? So we just have the idea of charge, which is charge moving. So you technically have a current, but it doesn't, it's not a parameter that we use in these calculations, okay? So that's how you find the equivalent capacitor for series. And then if this is the same Q, so if all of them have the same Q, what's different is the voltage. So C1Q, V1, V2, V3, and if you add all of this, you get V. Think of it as a conservation of energy for the voltage, okay? Something similar will be discussed with resistors in another lab. Now for parallel, let's take a look at parallel. For parallel, the voltage across each capacitor is the same. It's because the way they are plugged. This is a parallel setting. You see that? And then you can plug this to a power supply. So just like we had before, this is your V, the voltage supply. Let's say this is C1, C2, C3. So the equivalent capacitance, right? The way you find the equivalent is by adding all of those. So that means that the total charge is the equivalent capacitance times the voltage supply. This is important, all right? You want to relate, and that comes from the definition of capacitance, by the way. Now, this V is the same across each of these. So V, V, V. So what's split? Q3, Q2, Q1. Now, in the lab, if you were doing the lab in person, or even, yeah, if you're not in person, you cannot measure charge. You have ammeters and voltmeters. So they allow you to measure voltages and currents. So you can measure the voltage, and then you have the voltage and the capacitance, which is given, you can find the charge by using this equation, right? For each capacitor, you can say that Q3, for example, Q3 is equal to C3 times V. And V can be measured in the lab with a voltmeter. Okay, so let's take a look at the experiment and then let's see what values you're gonna have. Now remember, the values for capacitance are always small. So you're gonna be working with powers of negative 11, negative 12, negative 13, so picofarads. So you just be careful with that, okay? Now, if you click here, you will get the following. Oh no, that's a previous, what is it? I click already, it's weird. Okay, yeah. Is this the one I want? Yes. Okay, guys. So it's good that this happened. For this particular lab, you're gonna have to download the Java version of this because it's not in PHET technically. And then when you add it, you're gonna have these options. Okay. So you can have the multiple capacitors there. If you have an issue with that, please let me know. I haven't tested this in a Mac. I know Java works differently, so if you have issues, let me know so we can figure something out. All right. So in the lab, it says that we have to go to 1.5 volts. We're gonna do 3 in series. One 1.5. So yeah, the values are very small. 1.5, 2, and 3. So 1.5. It's gonna be, oh, there it is. 2. Oh, there it is. And 3. Oh, there it is. Then you're gonna grab the voltmeter and you're just gonna measure the voltage. Voltage 3, voltage 2, voltage 1. So in the manual, it says that you should do a table. You could do one in Excel. If you're doing it by hand, it's fine. But you can put here capacitors in series and then just show what values of C1, C2, C3 you have. This is 1.5 times E negative 13. E only. Yeah. And this is 2.0 E negative 13. And this is 3.0 E negative 13, right? Let's make this bigger. And then let's say you measure the voltage 1, voltage 3, voltage, that's it. V1, V2, V3. So you just write down V1 is 0.333. V2 is 0.5. Ah, what happened here? Volts. We can fix that. It's because it's coming from here. And then 0.667. So we can just highlight this, go to format cells, go to number. Oh, okay, fix it. So you can fix it with the formatting of cells. So this is 20, let's make it 20 as well. So you guys can see it. So there you are, right? So these are your values of voltage. And then you can use that to measure the experimental Qs, right? Or your Q1, Q2, Q3, right? You can Q1, Q2, Q3. The way you measure it is by doing C1 times V1. There. And this is in columns. Don't forget, right? If you want to write the whole thing better, Q2 will be, do it step by step, all right? For this one, just do this times this. And then you have the idea, right? So that's what you can do. The same with parallel. Oh, activate the voltmeter and the total capacity. Yeah, you can also activate that. That will give you the overall. And you can actually, that's your CEQ. So you're going to have to solve the circuit theoretically. It says here. We did this. Theoretically calculate. So what I did on the board, you're going to have to do it theoretically. All right? And then compare the values and discuss. Right? You can also find the energy. All right? And energy is here. And even charge. So you can compare everything. Charge, energy, and capacity. This is the total energy, total charge, total capacitance, total energy. So you can measure all that. To find the total energy, guys, let's show you here. If, for example, you have, for here, I see Q, the energy is 1/2 CV squared. That's the equation you want to use. And that's how you can compare the values of energy. All right? That's basically what you do. Let's do a parallel. Let's take a look. With a parallel is the same. We can just put 3 in parallel. Yep. 1.5 volts. And the values are the same. Yeah. So 1.5. Oh, it arranged it by. So if you get close to it, it does it for you. That's good. Notice how these values change. And they change because now this is in parallel. So C1 plus C2 plus C3 is the total capacitance. So that's what you have here. Now be careful because here is 10 to the negative 12. So if, for example, I were to add this, just to compare the value of the capacitance, sorry. There. So 3 plus 2 plus 1.5. Oh, what happened here? 3 plus 2 plus 1.5. 6.5, there it is. 6.5, that's the total. So simple, right? And to find the total charge, you will see this times V. And that would be 9.75 times 10 to the negative 12, or 0.975, 0.98 times 10 to the negative 12. This should be 10 to the negative 13, sorry, and then 10 to the negative 12. You divide by 10 here, okay? And that's how you value. So very easy to compare those values. The same with energy. So you're going to do the same procedure. You can measure the voltage and you're going to realize that it's the same. 1.5, 1.5, 1.5. So for parallel, it's not really that difficult, all right? You can do a similar table like this, and you will get the values that you need. You will do the same. And then this one is when you want to have the combination. All right, for the combination, you have to be a little bit more careful, but it's kind of the same. Two in series and one in parallel. Let's see which ones you're supposed to have. Yeah, so C1, C2. So C1, 1.5, 2, 3. So again, all these values change because, okay, let's see. If C1 and C2 are in series, you want to combine these two in series. So let's actually solve it so you can see what you are getting there. All right. So C1 is 1.5 times 10 to the negative 13. C2 is 2 times 10 to the negative 13. So you have C1 and C2. And of course, C3. Right? So these two are in series. To combine them and then parallel with that. 1 over C, let's do this as C. It's not equivalent yet. Look, these exponents, you know that the final result is going to have 10 to the negative 13. So you can just grab the 1.5 and the 2. You can do that. So then there's a nice algebra trick for two fractions, only for two fractions. C will be 1.50 times 2 divided by the addition, which is 3. That would be the C equivalent for the series one. So that's 3 divided by 3.5. 0.86. But remember, 10 to a negative 13 times 10 to a negative 13 farads or farads. Then you're going to add these two because these two are in parallel. This and this, when you combine these two, that one is in parallel with this. So you just add it. So the C equivalent is 3 times 3.86 times 10 to the negative 13 farads. Now, in the, yeah, it's the same value that you copy that. So that's basically how you do it. Okay, that's what you do. And then you are going to measure the same with a voltmeter, the voltages, and then using this, you can theoretically find the value of the charge on each. The value of the charge is not going to be the same for the parallel ones, but it's going to be the same for these two. Now, if you have them two in series and one in parallel, how do you distribute the charge? So the way you're going to do that is by realizing that when you have them in parallel, so these two and these are in parallel. So the voltage here is 1.5 volts. If you look at the circuit, the voltage on frame is 1.5, 1.50. So C times V give you Q3. Q3 is easy to find. Is this times that. Then how do you find Q here? Q1, Q2 are the same. Well, using C equivalent, you can find the total charge, which you also have to compare. It's in the simulation. But theoretically, you can find it. That Q total is C equivalent times 1.5. So if you find Q total minus Q3 is equal to the Q on these two because of conservation of charge. Okay? That's what you can do. That's how you do it. Okay? And all the values will actually match eventually, and then you can write your conclusions on this lab. Okay. Again, if something was not clear, please email me. Although I think this lab should be quite simple for most of you. And let's take a look at the individual questions. They're more theoretical than anything. Yeah, so 1 and 2 are conceptual. 100 volts battery is placed across a capacitive network, so a circle of capacitors of a 200, 680, and 1500. A circle of the maximum. Okay, look, either parallel or series. All right, you can just compare parallel and series. Don't go crazy with the combinations. Just compare the parallel and series for this. Then you can just find the charge, draw a series parallel. Okay, so that's basically what you did in the last section of this, like this. You have three capacitors in parallel and series, and you can like combine them. A capacitor value Ca is charged V1 and Cv is charged V2. If the two charged capacitors are connected with positive plates tied together and negative plates tied together, find the voltage and charge on each capacitor. Okay, that's not bad. That's basically just expressions. All right. Remember that if they are if the two charged capacitors are connected with positive plates tied together and negative plates tied together, if the two charged capacitors are connected with the plates tied together with the negative plates, with the positive plates tied together, and the negative plates tied together. Okay, so this basically is asking you if they are in series and parallel. Okay, so for these ones, you can assume if the positive plates are tied together and the negative plates are tied together, meaning that they are on top. Positive, negative, positive, negative. So if they are in parallel, you can redistribute the voltage. And the voltage on each will be the same. So the voltage V1 plus V2 for both, and then you can use that to find the charge on each. And this one will be in series. So that's basically what you have to do for this lab. All right, guys. So if you have any questions about this, please let me know. All right. Other than that, that's it for this tutorial. Have a good day, guys, and see you all later.